Okay, so I'm introducing, if I'm not wrong, Mark Swinburn.
Yep,
That's correct.
yeah.
Okay, and he's European Smart Metering and Appliance Vertical Team Manager at NXP Semiconductors, responsible for developing and delivering NXP technology solutions to the market, and he's specialized in smart metering, embedded MCU, security, NFC, voice, IoT, comms, and ML. Yeah.
Yes.
Then Mark, the floor is yours.
Thank you very much. Good morning, everybody. Thanks for joining our session. My name is Mark Swinburn, as I've already been introduced. I work for NXP. For those of you that don't know NXP, we're formerly Philips Motorola. I work in the Smart Energy Group for Europe. I'm the vertical manager. And today, I'm going to be talking about some of the challenges that if any of you have been fortunate enough to ever design a meter, some of the challenges that you may have seen and had to deal with, and possibly a new approach that using NXP you may be able to solve those problems. So I'm based in the UK, so no questions or comments or even jokes about Brexit, please. Let's stick to the script. So of the four challenges, the first one I wanted to highlight to you is, as I said, anyone that's ever designed a meter, first of all has to face the challenge of legally relevant and legally non-relevant, and that's a way where you have to separate the metrology, the billing, the metering from the non-sensitive data and part of your application. So, for those of you that are familiar with meter design, you'll be familiar with this concept of legally relevant, and what we have at NXP is a new solution where we can provide the isolation between the legally relevant and the non-legally relevant. And the result being that reapproval or changing your code, changing the operation of the meter is far more simplified. So the question comes, how do we do that? So it's a new approach. We've released a new device called the LPC 5500. It's based on ARM's latest core, which incorporates trust zone. So with trust zone, we get the isolation between the legally relevant and the non-legally relevant application code. This is done with the trust zone in hardware so that you can certify, you can prove, you can test that the isolation exists in hardware. What this also brings us is the ability to reduce the security complexity. Security is important to all of us. So reducing that is important to all of us today. And what we can also do with the new core is we can reduce power consumption whilst we increase performance. So I'm going to show you a little bit more detail about how we do that. But fundamentally, on our new chip, the LPC 5500, we're able to assign two cores. We have dual core architecture inside. We could assign, or you could assign, one of the cores to do the legally relevant, and then use the second core for the non-legally relevant. So you get the isolation, and yet you still get parallel operation, okay? So that was the first challenge, separation and isolation. The second challenge is how many of you can keep a secret, or how well can you keep a secret? So as we know, the security of any system is based on how securely you can keep that secret. If you keep a key stored in your onboard flash, then for $4,000 you can decap the chip, and if you take it to the local college or university, you can read the keys, okay? So we need a mechanism to address that challenge. So on the slide, you see security against cost. So the traditional mechanisms for keeping secrets in a chip, on the left-hand side bottom we've got ROM. ROM is very cheap, but it's not particularly secure from an optical perspective. Most people move towards fuses, electrical fuses. Again, a slight increase, but better security because you cannot repair them or reinstate them. Then we looked at flash EEPROM, and then finally anti-fuses, which is probably the most secure, but it does come at a cost. So the current solutions that you might be familiar with are all, let's say, physical alteration, and they're all optically visible, okay? So we've looked at solutions, and the approach we're using is what we call SRAM PUF. I'll explain what PUF means shortly, but essentially SRAM puff is only created on the device while the device is powered, and there are no traces, certainly optical traces, that you would have used to discover them in the past. So if you can keep a secret, you can use the puff to do that. So how do we protect these keys? So physically unclonable function is what puff stands for, PUF, puff. So when you encrypt using a key, you need to store it somewhere, okay? So if an attacker is able to access your device, your meter, even if they just read out the flash, don't do anything with it, and reprogram that flash in another device, they've copied your meter. And as I mentioned to you, if you pay $4,000 and have the top taken off your chip, then you can also read the key, okay? So the puff, the physically unclonable function, what does that do? We use process variation in generating transistors, and the process variation that we get is able to create unique logic levels on the SRAM cell when they get manufactured and when we first power them on. So every time this SRAM block switches on, it generates a unique pattern, like a fingerprint. The unique pattern is reproducible. So once it creates the number, it always creates the number. These numbers are, whilst they're random, they're repeatable. And each key is unique to each device. And the key only exists while there is power applied to the device. So if you switch it off, you lose the key. And as I said to you, they are not optically visible. Okay? So what does that mean? It means that we create a digital fingerprint for every device that's unique. The secret key is not visible. It's hidden on a private bus. And there are some additional countermeasures that we apply so that you can't discover them using some side channel attacks that are quite common. So puff, it might be a new word, physically unclonable, and I say it's ephemeral and you can't use optical techniques to discover them. So the third challenge is always security, because security can be quite complicated, especially if you're not an expert, not been doing it for some time. And we at NXP with this chip, we're able to solve some of that complexity. So we talk about trust zone, which I mentioned earlier on. That brings us that isolation that your meter is going to need to go through approval. We think about secure boot, which is a mechanism to ensure that your firmware, only your firmware, is used at boot time. We think about some of the security primitives that we use to give you privacy. So this is all about encryption on board, that we have acceleration, encryption, decryption, random number generators. The secure key storage gives us the confidentiality that you need. So if someone's able to at least look inside the chip, they can't discover any of your secrets. Key to meter design is always OTA. So there are mechanisms on this chip in hardware to allow the secure update, to make sure that that's not a backdoor mechanism for people to gain access to your meter. And then the last one, which also is relatively new, is a secure debug. Normally when we make meters, we tend to lock them so that no one has access, but then how does the maintenance guy, or when it gets returned from field, how does that access be granted? So we've got a secure debug mechanism on this chip as well, which solves a few problems. Okay, so the next challenge is all about performance and efficiency. For those of you that are not familiar with the M33 core, it's the latest core from ARM. It has some advantages over what we would see as the more familiar meter cores, the M0, the M3s, the M4s. The M33 is a revitalized core from ARM, and as a result we get more performance per clock. We use some tightly coupled blocks that go with the core to improve both performance and calculation. So as part of metrology, quite often we need to understand and measure the mains quality, and we can do that with some of the acceleration on board, so we can accelerate maths, FFT, and some crypto as well on board. So a lot of this extra work is done in hardware, so it's not taking clock CPU cycles. And also, because it's at 40 nanometer, it means that we can reduce the power consumption, and we can also make more devices on a wafer, which ultimately brings the cost down. So it's all about optimizing the performance and the cost. So a very brief look at what it looks like inside if you took the top off. So it's based on the M33 core, as I said. It has 2 cores, so it's dual. We have customers that use 1 core for legally relevant and the 2nd core for non-legally relevant. So it's a great way to partition your application. And then we've got the security hardware accelerators as well. Okay, so this the LPC 5500 is a family of devices. And we've launched these devices in a scalable way, both in flash, SRAM, and packages, so that we can target particular markets. So for the higher end, more resource intensive, where we have maybe a HMI or gateway, then we've got the high end family based on the 5500, the S6, 7, and 8. And then when we look at the traditional electricity meter, we have a slightly different family with a slightly different cut of the silicon to support the key functions of electricity meter. And then finally we have, let's say, the lower performance end, where we would consider perhaps water meters and gas meters, where we have the LPC 55 1X, 2X, and 3X. And we've actually added some analog functionality on there, which will save you on your BOM cost as well. Okay. So, for us, the key takeaways for you guys, as I say, if any of you have ever sat down and challenged yourself to design a new meter, the M33 core is based on 14 nanometer technology. So, as I say, we keep the energy consumption down, whilst we're able to make more on a wafer, so we get the lowest power, performance, and cost. Trust Zone from ARM gives us that ability to separate in a certified way the legal and non-legally relevant. The dual-core architecture with the DSP will allow you to do additional maths, FFT, signal analysis in hardware. And with the hardware accelerators for cryptography, then you're able to do that again in an assured and managed way. And with the enhanced security, with the rollback and the firmware verification, then all that is done in hardware, so we reduce the complexity. And then finally, at 40 nanometer, we benefit from the process technology. So we're burning around 35 microamps per megahertz. So again, we're always driving down that energy consumption. So, if you are interested, and I hope you all were, and you want to know more, then these slides are available, but certainly go on the nxp.com website, and you will find a host of information. So, I hope that was interesting to you guys, and you can see that it is a different approach to the challenges that you are going to find when you sit down and design your next generation smart meter. Okay, thank you very much.
Time for a couple of questions to the speaker. I think this morning there was
no Brexit questions, by the way. No Brexit.
No Brexit questions. Maybe we'll need to bring some coffee here to this audience because we have hundreds of people and nobody has questions. That is amazing. Nobody has any questions? You're not worried about anything in your company? Wow. Okay.
So I guess a question for the audience then. How many of you are actively designing smart meters?
Mm-hmm. Raise up your hands.
Okay. Yeah. So we've got some guys. So the challenges, do you agree with the challenges? Yeah? How much pain on a scale of 1 to 10? So when we think about legally, non-legally relevant.
Can I answer to this one?
That's a biggest challenge. That find a way to make them work together, to communicate between them and to isolate legally relevant.
Yeah.
So that's a huge question.
Yeah. So you saw the way that we could do it with Trust Zone. Does that make sense to you?
Of course.
Good. Yep. Good. Okay. So that was challenge number 1. Any other challenges?
There are a lot of challenges.
So I only could cover 4 today, right?
Yes, but probably most important.
Yeah.
Any other questions? At the end, I can throw it to the end, no problem. No more questions? Okay.
Okay. Thank you all again. Thanks.
Thank you so much. Yes. Thank you very much. Thank you. Okay. So now we run to the next speaker, to Mait Rahi. Yes. So Mait Rahi is smart metering